Also on the periodic table, underneath the element symbol is another number. Those are mostly not nice whole numbers. You'll notice that some of them are whole numbers in parentheses. Those are radioactive elements, and we're not going to worry about those. But mostly you'll see numbers like this guy down here, 35.45 or 12.01, 6.941, not nice whole numbers. Those are the average atomic masses of atoms for each of those elements. The percentages, remember that slide I showed you with neon and how 90% was the one and like 0.27% was the other. Those percent abundances are relatively constant no matter where that sample of element came from. And so we can calculate an average mass of atoms. It's quite unusual to deal with individual atoms. Mostly we deal with large numbers of atoms. And so then the average mass becomes important, right? If we were doing something with all of you in an elevator or on a trampoline or something that had a weight limit, we would care about the average mass of people to figure out how many people we could let on there, right? If you're dealing with who can ride the camel at the zoo, then we're concerned about the actual mass of one person. But most of the time with atoms, we're dealing with a large number, and so we're interested in the average. Normally, when you calculate an average, you take the mass of each thing and you add them all up and you divide by the total number of atoms. Well, if you're dealing with 3 gazillion atoms, that's not going to work. And so we use a weighted average to make the math easier. So if we look at naturally occurring chlorine, 75.77% of chlorine atoms are chlorine-35, and 24.23% are chlorine-37. And these are the masses in atomic mass units of each of those isotopes. You'll notice that 34.97 is very close to 35. 36.97 is really close to 37. So if you're just dealing with round numbers, you can look at this mass number and say, oh, well, that isotope weighs about 35 atomic mass units. This one's about 37. So instead of adding up a whole bunch of these and dividing by some obscenely large number, we use percentages converted into fractions. So 75.77% is 75.77 out of 100. That is equivalent to 0.7577. This fraction here is just the percent divided by 100. So 0.7577 of them are the 34.97 atomic mass units. So we take the fraction, we multiply by the mass of that individual isotope. And then we take the other fraction and multiply by the mass of the other isotope, and we just add them together. There's no dividing, and we get the average mass. The average has to be between the highest and lowest values. So if you do a calculation like this, and you come up with something that's smaller than 35 or larger than 37, go check your calculations because you did something wrong. This mass is between this mass and this mass. But it's not a simple average where you just took the two numbers, added them, and divided by 2. So here's the general equation to calculate atomic mass. And I promise you there will be at least one question about this on the next exam, exam 2. This is not, though, a big deal in Chem 3A. So if this part is just blowing your brains and you're like, I can't even think about that, this would be something that you could skip and still pass the class. Significant figures are pretty important. Dimensional analysis is critical. You can't skip that. So I'm just letting you know. This is not something to obsess over, but give it a shot. The fraction of the first isotope times its mass. the fraction of the second isotope times its mass, the fraction of the third isotope times its mass. However many there are, you do the same thing, you add them all together, and that's your answer. Let's do an example. Magnesium has 3 naturally occurring isotopes. It gives us the masses, and it gives us the percentages, and it asks for the average atomic mass of magnesium. So we're going to take these percentages and convert them to decimals. So 0.2399. This one, that's the first mass. It goes with the first percentage. Wait a minute. That was wrong. We don't convert the mass, we convert the percentage. Okay, 0.7899. Take the percentage and divide by 100, multiply by the mass. 23.99 AMUs. Okay, and then this is the second percentage. That's the second mass. So we convert 10% into a decimal. We multiply by the mass of that isotope. And then the third one is 11.1%, 0.1110 times its mass of 25.98. And then we're going to add them all up. So 0.7899 times 23.99 plus 0.1 times 24.99 plus 0.111 times 25.98 equals. My calculator is showing me 24.332481 atomic mass units. Significant figures can get a little sticky here, so we're not going to worry about it too much. The way it works out is basically you're looking for the number with the smallest number of significant figures. So here this one has, all the masses have 4 significant figures, and all the percentages have 4. So then we're going to round this to 4 significant figures, and we're going to call this 24.33 atomic mass units. Is that a reasonable number? Is it between the lowest and the highest? Mm-hmm. Yeah, that's a really good sign. What's it say under magnesium on the periodic table? 24.31 or 24.305. Should we freak out because this isn't exactly the same? No. The difference is in the uncertain place, and so it's okay. Any questions? Yeah.
So, those numbers for the magnesium, those are isotopes? Or where did we get those numbers, the 23.99, 24.99?
This sort of information would have to be given to you.
Okay.
You're not going to be able to pull it off the periodic table.
Okay.
They'll have to give you the percent abundances. They'll have to give you the mass of each isotope. The only thing they might possibly mess with you on is they might give you all but one of the percentages. All the percentages have to add up to 100. Okay, so if they say there's 2 isotopes and 75% is this one and the other one weighs this, and they don't give you the other percentage, 100 minus 75, it's 25. In the next level, in Chem 1A, they'll mess with you in all sorts of fun ways. But here we're going to keep it simple and do straightforward calculation. Any other questions? There, we finally finished chapter 4.